Greetings and welcome to GILFORD'S lectures. So today we are going to be looking at the second part of the tutorial questions on differential equations. Our instruction says that let us show that the function y equals f of x solve the given differential equations. We have a, b, and c. And in a, b, and c, we have the function y and we have a given differential equation, and we are required to check that the function y solves the given differential equation. I hope you can see the functions y in a, b, and c, and these are your differential equations. Now, let us look at the solutions. We are going to use A as a sample case, but the methodology adopted to solve A will be the same applied for B and C. So generally, to solve this problem, you must first of all identify your function y, which is in terms of x, and you identify your differential equation, where this is the right hand side of your differential equation and this is the left hand side of your differential equation. For your function y, you aim at differentiating it and replacing it in the left hand side of your differential equation. So you are going to replace it in the left hand side of this differential equation. Alright, this is A, which is y equals 5 on 3x cubed plus 4 in x plus c, where c is a constant, such that x dy dx equals 5x cubed plus 4. So for you to be able to solve this differential equation, you must first of all differentiate the function y. So let's differentiate the function y. If we differentiate the function y, dy dx will therefore be equal to 5x squared plus 4 on x, and when you differentiate the function, when you differentiate the constant c, you obtain a 0. Now we have obtained dy dx. We are going to replace this dy dx on the left hand side of this equation. So it will therefore imply that x into dy dx, which is 5x squared plus 4 on x, will be equal to 5x cubed plus 4, which is equal to the right hand side of our differential equation. Hence, you conclude that y equals 5 on 3x cubed plus 4 in x plus c solves our differential equation. Alright, for B, you are going to do same. The only difference is that the function y and the differential equation are different from that which we saw in A, but the methodology is the same. So differentiating the function y with respect to x, you obtain a cos x, and when you differentiate -1, you have a 0. So replacing dy dx in the left hand side of our differential equation, you obtain sin x into dy dx, which was given by a cos x obtained above, divided by 1 plus the function y, which is a sin x minus 1, which is equal to a sin x cos x on a sin x. So a is going to be taken out, sin x is going to be taken out, and you are going to be left with cos x, which is equal to the right hand side of our differential equation. Hence, the function y solves the differential equation. So the function y solves this differential equation. Now let us look at the very last function, or the very last question, c. So you are going to differentiate your y to obtain c e to the x plus, here you are going to apply the product rule, so you have d e to the x plus dx e to the x. But you observe that if you end it here, then you are only going to have a replacement for dy dx. Essentially, for you to be able to have the differential or the replacement for d squared y dx squared, you must differentiate dy dx to obtain a second derivative. So differentiating dy dx to obtain d squared y dx squared, you obtain c e to the x plus g e to the x plus d e to the x plus dx e to the x, which essentially is equal to c e to the x plus 2d e to the x plus dx e to the x. Now we are going to replace d squared y dx squared and dy dx in our differential equation. So when you do that, you are going to obtain c e to the x plus 2d e to the x plus dx e to the x minus 2 into c e to the x plus d e to the x plus dx e to the x plus our y now, remember to close your bracket, c e to the x plus dx e to the x. So we cannot just allow this equation like this. Actually, we must put an implication sign here. So this therefore implies that we are going to have 2c e to the x plus 2d e to the x plus 2dx e to the x minus 2c e to the x minus 2d e to the x minus 2dx e to the x. Essentially, all of these 2c e to the x will subtract this other 2c e to the x, same with the 2d e to the x, and same with the 2dx e to the x. So all of this will be equal to 0, which is equal to the right hand side of our differential equation. So we have solved for a, b, and c. Remember that the simple rule here is just to differentiate the function, and depending on if your differential equation is first or second order, you are going to differentiate the function either once or twice and do your replacement in the differential equation. So thanks very much for watching GILFORD'S lectures. I believe you loved the video. Please subscribe to my channel, share to generate more traffic on the channel.